Right, this is the VIEW program. We're doing pre-calculus and we're on topic 2, which is factoring. So when we talk about factoring, no matter how complicated problems get, we can really essentially boil it down to 5 steps, sort of, kind of, quasi 6. So let's scroll over to my factoring checklist. Okay, so when you're factoring, the first thing, the thing I would call the 0 step, right, is if you're factoring an equation, you have to make sure one side of the equation equals 0. And we'll get to that when we talk about topic 3, which is solving for zeros and solving equations. But I'm just throwing that in there now that technically, before we do all the steps, we should keep in mind that if we have an equation, we should set one side of the equation equal to 0 by moving terms around. Okay, beyond that, the first thing we should look for is a greatest common factor, a GCF. If something has a greatest common factor and you can factor that out, you're going to make the rest of the problem easier. Sometimes that's not the only step. Sometimes that is the only step. But either way, you make your life a lot easier by doing that first. The next thing to look for is if your expression is a binomial, meaning it has 2 terms. There are 2 familiar patterns that we see in binomials. We call them special binomial patterns. One is called a difference of squares. That one looks like a squared minus b squared, meaning, because remember, math things are either named after a person, like Pythagorean theorem or Pascal's triangle, or they're named after exactly what they are, in this case, a difference, meaning subtraction of squares, right? And that's going to factor into the quantity a plus b times the quantity a minus b every single time. So it's good to look out for that. The other one is a sum or difference of cubes, and I'm not going to go into a ton of detail on this, but it could be a sum or difference, so you'll see a plus or minus, and it's of cubes, so you'll see a cubed plus b cubed. And the pattern here is a squared, b squared, and then you keep the sign, meaning it's plus over minus, so the same thing here. If it was a plus, it'd be a plus. If it's a minus, it's a minus. Change the sign, so minus over plus. Always a positive. So you don't have to have this memorized. Most people probably don't, but I thought I'd throw it on here, and I'll erase it in a minute. But if you want to put it down in your notes, that's the sum or difference of cubes. You absolutely need to have the difference of squares memorized. Sum or difference of cubes probably depends on your situation, but I would say that the difference of squares is super duper key. The third thing to look out for is if something is a quadratic trinomial. What we mean by a quadratic trinomial is ax squared plus bx plus c. Quadratic, meaning the highest degree is 2, and trinomial, meaning it has 3 terms. Quadratic trinomials tend to factor by doing what we call unfoil, right? And you've learned a bunch of different ways to do this. You've learned to do, a lot of people learn like product sum charts or like t-charts or sort of cross methods. I know a bunch of different methods. They all do essentially the same thing, which is they are the opposite of distribution by foiling. So I'm going to call this unfoil. The fourth thing to look at is if we have an even number of terms. So, for example, if I had something like x cubed minus 2x squared plus 9x minus 18, see how there are 4 terms? Then I might be able to factor by grouping, and that's why I wrote try grouping. And we'll do some examples of that in a sec. And then if all of those fail, the Hail Mary pass, if you've ever seen a Hail Mary pass in football, it's the throw you make at the last minute when the buzzer's about to go, when you're just trying to make that touchdown. The Hail Mary pass of factoring is synthetic division, and we're going to get to that too. But so what we're going to do is I'm going to leave this checklist here. I'll erase the formulae, and we're going to walk through examples that do all of these things. After we go through the examples, then you're going to do some practice problems on your own. All right, so let's start with example 1. So we're going to fully factor each expression in all of these examples, okay? So we're going to do example 1. We have a 1a, which is a 5x cubed plus 15x squared. We have a 1b, which is an 18x minus 10. And then we'll talk about example 2 over here in a sec, because we'll just free up some space. So 2a is going to be a 4x squared minus 9. 2b is going to be a 2x cubed minus 50x. And example 2c is going to be an x to the 4th minus 81. Okay, so let's start with example 1. So we have a 15x cubed plus 15x. This isn't an equation, so I don't have to worry about one side equaling 0. Remember, an equation is when you have an equal sign. This is an expression, no equal sign. So the first thing I should do is look for a GCF. So I noticed that 5 and 15 both have a factor of 5 in common, so I can definitely take out a 5. But I also noticed that x cubed and x squared mean I could take out an x squared. So my GCF is going to be a 5x squared, And what's left over is going to be what happens when I divide these things by 5x squared. When I divide the 5x cubed by 5x squared, I'm just going to get an x, right? Because I'm dividing by 5, so the 5's gone, and I divide the x cubed by x squared, and so essentially I subtract their exponents, get an x, and then I'll end up with a plus 3 here because I took the x squared entirely out and took the 5 out, which leaves me just with 15 divided by 5, which is 3. So I have a GCF, I have leftovers. That's not a mathy term, it's just what I call them. So my answer is 5x squared in the front, and then in parentheses, x plus 3. And that's it. There's nothing left to factor here. X plus 3 is a binomial, but it's not one of the special patterns, so we're done. When we look at 1b, I have an 18x minus 10. So I notice there's not an x in the second term at all, so there's definitely not an x coming out, and the biggest factor that both 18 and 10 seem to share is a 2. So if I take out a 2, I'm left with 9x minus 5, and that's it. I have a GCF of 2, I have a 9x minus 5 left over, and that's fully factored. All right, so let's move on to example 2. So I look for a GCF first. I see 4x squared minus 9. 4 and 9 have no factors in common, right? 4 is just 2's and 9 is just a bunch of 3's, right? And there aren't x's in common either, so I can't take out a GCF. I then look at the next thing on my checklist, which is binomials, and this does look like a special binomial pattern. In fact, this is a difference of squares, right? I can tell it's a difference of squares because 4x squared is a perfect square. It's 2x, quantity squared, minus, and then 9 is a perfect square. It's a 3 squared. So in this situation, my a is 2x and my b is 3. So this is going to factor into a plus b, which would be 2x plus 3, a minus b, which would be 2x minus 3. And that's what this factors into. Now, if you're not sure you're right, you can FOIL to check. If you do first, you're going to get 2x times 2x, which is your 4x squared. Outer is going to be a negative 6x, and inner will be a positive 6x, which is not an accident. In a difference of squares, the OI, the outer and the inner, will cancel. And my last term should be negative 3 times 3, which is a negative 9. Okay, let's move on to 2b. 2x cubed minus 50x. Now I notice that it's a binomial, but before I look at any of the special binomial patterns, I should look for a GCF. I see that the 2 and 50 have a 2 in common, and that both terms have an x. So it looks to me like I can factor out a 2x and be left with x squared minus 25. Now, I have a GCF, but it turns out that my binomial is a special pattern. Unlike what we saw previously, if you look over at example 1, when I took out a GCF and my binomial was just a boring old expression, here, this binomial is a difference of squares, right? Because x squared is a perfect square, and 25 is a perfect square, and I'm subtracting them, which is what makes it a difference of squares. So I'm pretty sure I keep this 2x in front, and then I can factor x squared minus 25 into x plus 5, x minus 5. Because again, in this situation of the pattern, my a is x, and my b is a 5, because the backseat is b squared, so b would be 5. Now, 2c is a little tricky, and I'm going to give myself a little bit of space to do 2c by coming up here, because I know it's a little harder to see things at the bottom of the board. So when we go to do example 2c, x the fourth minus 81, well, there is no GCF. The first term is all x's, and the backseat is all numbers, so there's no GCF. So it's got to be one of these special binomial patterns. But it doesn't immediately look, it's definitely not a cube, right? Because I see the next, the fourth is not a cube, and an 81 is not a cube. It could be squares though, right? X squared squared minus a 9 squared, well, that would be a difference of squares, right? And it would factor into a, which is x squared, plus b, which is 9, and then a, which is x squared, minus b, which is 9. Well, this guy is what we call prime. He doesn't factor. X squared plus 9 is a special thing. It's called a sum of squares, but a sum of squares does not factor over the real numbers. It would only factor in imaginary numbers, the letter I. So this guy, however, is still a difference of squares. So what's going to happen, because I was asked to fully factor, I keep this prime factor the way it is, but my x squared minus 9 is another difference of squares, where a is now x, just like it was in a previous problem, and my b is 3, because 3 squared. So I get x plus 3, x minus 3. So when I fully factor, I get 3 factors, an x squared plus 9, an x plus 3, and an x minus 3. Remember, that key word here in the instruction is to fully factor, not just factor. Okay, so let's move on to example 3. All right, so as you can probably predict, example 3 is going to involve quadratic trinomials because that's the next step on our checklist. So in example 3, we're still fully factoring. Example 3 and example 4 are both quadratic trinomials, so we're going to talk about what that looks like. Now, I don't factor quadratic trinomials the same way everybody else does. A lot of people have a much more rigid sort of structure and pattern. I'm going to argue that it's a lot about pattern recognition. So, when I go to do 3a, right, I'm going to factor x squared minus 11x plus 10. So here's the trick to factoring. The first term, your x squared, is the f in FOIL. What that means is that the two front seats, the only way I can get an x squared is if the two front seats in my binomials are both x's, right? The only way I'm getting an x squared is if it's x times x. Now, there are a bunch of different ways to get a 10. I could get a 10 with a 1 and a 10, or with a 2 and a 5, right? Because the last terms would be multiplied. But the trick here, right, is that I know some other information. So I know it's either a 1 and a 10 or a 2 and a 5. And I can gauge that information by looking at this oi in a second. But this plus sign at the end tells me that they have to have the same sign. Because the only way that I could get a positive in the backseat is if whatever these two backseats are here are the same sign. A negative times a negative would give me a positive, or a positive times a positive would give me a positive. So once I know they have the same sign, I can actually find that sign by looking at the sign in front of the oi part. These both have to be minuses. They have to be the same sign because they come out as a positive 10 when I multiply. Once I know that, I can kind of logic my way through. If I used a 2 and a 5, I'd get a negative 2x and a negative 5x, which is a negative 7x, and that's not right. So I try, what if I use the 1 and the 10? It doesn't matter which one I put in which set of parentheses because a multiplication is commutative, so x minus 10 in front of x minus 1 would be the same. So I get this as my guess answer, and then I should always check. It can be something that you do internally in your head, right? But it's something you should do because you'd be surprised the number of times that we accidentally factor wrong. As you move forward in pre-calc and calc, factoring wrong is going to be a big deal because factoring is one of the early steps in a very long calculus problem, and if you don't factor right, it's like a domino effect. Everything else goes wrong. So when I check really quickly, I check that the first is right. So first would be x times x, which is x squared, right? Outer would be a negative 10x. Inner is a positive, or a negative 1x, and last is a positive 10. So sure enough, when I put these guys together, I get x squared minus 11x plus 10, which is what I was supposed to have. This is my factored answer, right? So let's try 3b. So 3b is going to make this just a notch harder, and the way that's going to happen is that the term at the end is going to have a negative. So I'm going to get an x squared plus a 4x minus a 12. So same rules apply. My x squared is my f, the middle stuff is my oi, and the last term is my L, right? So when I factor this, I know the front seats have to be x and x, because that's the only way I'm getting an x squared. We'll talk about what happens when that leading term isn't just an x squared in a minute. Now the back seats, 12 is tricky for a bunch of reasons. Reason number one is that 12 has a bunch of factors. It could be a 1 times a 12, a 2 times a 6, or a 3 times a 4, right? I don't know which one of those three combinations it is, but it could be one of them. The other thing that makes this much, much harder is that in this instance, this minus tells me that these things have opposite signs. So one of them is a minus and one of them is a plus. So I can't just assume that they're the same sign, and now it does matter which number goes in which spot. So now I look at these combinations, and I think to myself, which of these combinations would give me a positive 4 if they had opposite signs? And I say, oh, it's the 2 and the 6, right? Because a negative 2 and a positive 6 would give me a positive 4, right? So when I FOIL to check this, right? My first term is x times x, which is x squared. The outer term is a 6x. The inner term is a negative 2x. And the last term is a negative 12. So sure enough, when I put all this together, I get x squared plus 4x minus 12, and I am correct. This is my answer, right? So if you have a different method that you use to factor quadratic trinomials, that's great, and I'm fine with it, and I certainly don't want to change your method. What I will say is that most of those other methods that you use aren't as quick as just being able to spot how the patterns work. Now, they may be more reliable if you find that you tend to make errors. So I don't care how you factor. Most of your teachers probably don't care. All we care about is that you do it effectively on your own. So be right and then be fast, right? It's more important that you're right first, then fast, because right and wrong is kind of useless. Let's do 4a. So 4a is 2x squared plus 5x plus 3. And 4b is 9x squared plus 66x plus 21. Okay, so let's walk through 4a. So when I look at this, it's a quadratic trinomial. There is no GCF, right? I can't take a number out of all of these. 2, 5, and 3 are all prime. They don't all have an x. I should have checked that in the last one, but I didn't. My bad. I knew there wasn't a GCF because I wrote the problem. Kind of cheated. So now I'm in a little bit of a different situation here because my first term, the only way to get a 2x squared is if one of my front seats is a 2x and the other one is an x. Now the reason that this matters is because now it very much does matter which numbers go in the back seats because it's not just an x at the front anymore. They're different things. Now, the nice thing about this problem is the only way to get a 3 is a 1 and a 3, so I already know ahead of time those are the two numbers going in the parentheses. I also know from this that because it is a positive 3, this tells me they have to have the same sign, so I can use whatever signs at the front to put the sign in place. So really, my entire job now is to figure out which seat gets the 1 and which one gets the 3. So you can do this a couple different ways. You could just kind of try it in your head and see what happens. I noticed that if I put the 3 opposite the 2, I get a 6x and a 1x. 6x and 1x is 7x because they have the same sign. So the 3 can't go over here. So it has to be a 3 here and a 1 here, and then I check. When I FOIL, my first seats are 2x times x, which is a 2x squared. That's correct. My outer and inner together are a 2x and a 3x, which together is totally a 5x, so that's correct. And my last term is a 1 times a 3, which is a positive 3. So this is my answer. Now, I'm showing a lot of work here that, to be honest, I wouldn't be showing if I were doing this in my head. As you get good at doing this, you can do this internally without a whole lot of thought. Let's talk about 4b. So in 4b, the first thing I should have done in every one of these problems, although I kind of cheated because I knew they didn't have one, is look for a GCF. 4b does have a GCF, and taking it out now makes all of the other stuff way easier. There's a 3 in all of these. So if I take out a GCF of 3, what's left is a 3x squared plus 22x plus 7. That's way nicer because 9 has a couple different factors, so does 21, but suddenly I'm looking at 3s and 7s, which are really easy because they're prime numbers. So I still have this 3 in front, right? But when I look at the first term of my quadratic trinomial, it has to be a 3x times an x, because the only way to get a 3x squared is if one of the terms is a 3x and the other one's an x. I look at the back seat and see that it's a 7. That has to be a 1 and a 7. There's not a lot of choice. In fact, it's even easier than that because I see that this plus sign is here, which tells me the signs have to be the same, so I look here and see that they're both positive. So basically, the only question mark is which seat gets the 1 and which one gets the 7. Well, you can kind of tell by looking at the 22 that I really want a 21 out of this. So if I put the 3 and the 7 in opposite sets of parentheses, I'll get a 21x and a 1x, and that's my 22. Now you could FOIL this to check, right? And again, this can be internal. 3x times x is my 3x squared. That's right. 3x times 7 is a 21x plus another 1x. There's my 22. And my back seats are a 7. So this is my fully factored expression. Cool. All right. We're going to move on to example 5 and then example 6, and that'll be the day. And then we're going to go ahead and have you do some practice problems. So in example 5, we're going to look at factoring by grouping. So example 5, which is going to be grouping. All right, so we have 5a is 4x cubed minus 12x squared plus 5x minus 15. And 5b, if I can squeeze it over here, we'll see, is a 9x cubed minus 27x squared minus 4x plus 12. Okay, so here's the concept behind factoring it by grouping. So you see that I have an even number of terms, 1, 2, 3, 4, and that I don't have any GCF because the easiest way to spot there's no GCF is look at these two coefficients. You've got a 4 and a 5. They have no numbers in common, and not all of these terms have an x because of the 15, so that's it. So factoring by grouping is sort of like walking into a party. So let's say your friend invites you to a party, and then your friend totally ditches you. And for whatever reason, you can't get an Uber or a cab, or you can't walk home. And so you walk into this party and you know nobody, right? So if you're anything like me, okay, so I'm going to be honest, I would figure out where the food table is and walk over and hang out around the other people that like to eat. But if you're anything like me, you look for somebody that has something in common with you. You say, oh man, I like the Eagles and that person has an Eagles hat. Or, oh man, I really like the X-Files and that person is wearing a nerdy like sci-fi 90s shirt. Awesome, right? So factoring by grouping is sort of that idea. The concept behind factoring by grouping is that these two guys group together and we find a group GCF, and these guys separately group together and they find a group GCF. So if we look at the first two, the group GCF, just these two, have a 4x squared in common, right? I can take out a 4x squared, and what would be left if I did that is an x minus 3. If I do the same thing, so this guy was like a group GCF, right? And if I do the same thing on the back, these guys have a positive 5 that I can yank out, right? And sure enough, what's left is an x minus 3. Again, I took out that group GCF. Now, what you'll notice is after we take out the group GCF, there is this weird underlying GCF. They both have an x minus 3. So if I take out that x minus 3, right, this new GCF that was right there, what's left is the 4x plus 5. 4x squared plus 5, my bad. And that is factored. Now, you do need to double check that your binomials don't factor any farther, right? Further, rather, it's extent, not distance. Anyway, so 4x squared plus 5 is a sum of squares. That's prime. It doesn't factor. And x minus 3 is also not anything squared or cubed. It does not factor. So that's my final answer. Now, when we go to look at 5b, we're going to do the same thing, but this one is going to factor a little bit further. So again, I notice there's no GCF. The 9 and the 4 are big hints. The fact that some terms have x's and others don't is another big hint. So if I do a group GCF here, these guys have a 9x squared, but what's left is an x minus 3, right? Didn't mean to make both of these minus 3s, but oh well. And then when I look at the second one, these guys have a group GCF of a negative 4, and what's left is another x minus 3. Not an accident that here, and again, didn't mean to make them both x minus 3s in this one and the last one. If I take out that x minus 3, what's left is this 9x squared minus 4. But in this problem, I'm not done. And the reason I'm not done is that this red factor is a difference of squares, right? 9x squared is a perfect square. It's 3x times 3x, right? And 4 is a perfect square. It's 2 times 2. So I need to factor that red factor one more time, right? So I have this x minus 3. It hasn't changed. And then this red factor is going to factor into a plus b, which would be 3x plus 2, a minus b, which is 3x minus 2. And this is my fully factored 5b. All right, we're going to do one last example, and then you have 12 practice problems. So, example 6 is what we do if we have completely run out of options, right? And that is synthetic division. So, we are going to factor 3x cubed plus 8x squared minus x minus 10. So here I have an even number of terms, but grouping is not going to work. And the reason I can tell that, and you could try it, but for grouping to work, and if you look at the last examples in example 5, you'll see, if grouping works, the ratio of this to this is the same as the ratio of this to this. If you look back at example 5, you'll see that in 5a, the ratio of the first two terms was a 4 to a negative 12, and the next two terms was a 5 to a negative 15. Well, those are a ratio of 1 to negative 3. They're the same ratio. This is a 3 to an 8, and a negative 1 to a negative 10. They're not the same. And you could see that anyway. If you tried grouping, it would fail. Because in order for grouping to work, so I'm just going to show you. I'm going to try grouping. I'm going to show you that it's going to fail. If I took out a GCF here, it would be an x squared, and it'd be left with a 3x plus 8. If I took a GCF out here, it would be a minus 1, and I'd be left with an x plus 10. See how these are not the same? Right? For grouping to work, they have to be the same group, and they're not the same group. So grouping doesn't work. So when grouping doesn't work, we then do a thing called synthetic division. So synthetic division is a shortcut for doing long division of polynomials, but it also gives us a cool trick for factoring. So basically what we're going to do is we're going to take factors of this, right? We're going to take factors of 10 starting at 1 and the negative 1, right? So plus and minus those factors. And we're going to do synthetic division to see if we get a remainder of 0. If a remainder is equal to 0, then x minus whatever that number is is a factor. So I'm going to go ahead and start with the obvious guess, which is 1. So this is sort of like doing, if you ever played that game Battleship, this is sort of like playing Battleship. You guess something that you think might be a hit. Your goal is to get a remainder of 0. So let's see what happens. So if you remember the way synthetic division works, you put your divisor right here, your 1 here. In this case, it would be the a that we'd, and then you write the coefficients of this polynomial at the top with a 0 anywhere that you're missing something. So see how I have an x cubed, and then an x squared, and then an x, and then no x at all? I'm not missing anything. If I were missing something, I'd need a 0. So the way we do synthetic division is we take this first number and we drop it all the way down here. We then do top number times the 3 and add straight down to get an 11. The top number times the 11 and add straight down to get a 10. The top number times the 10. So again, I'm writing these numbers up here, right? The top number times the 10 would give me a 10. When I add straight down, I get a 0. So this is my remainder. And if you get a remainder of 0, what that tells you is it tells you that your divisor, that if you used 1 as your divisor, it tells you that x minus 1 is a factor, and that what's left, if we start at the remainder and work backwards, is the number, the x, and the x squared. What's left is a 3x squared plus 11x plus 10. This is a quadratic trinomial that I can now factor. So essentially, the reason I said it's like Battleship is that when you get a number that works, in this case, the first number I tried worked. If you get a number that works, then you can more easily factor the rest. Just like when you play Battleship and you get a hit and you know that you've hit the ship, you then have a better idea where to guess. You guess things to the left or right or up or down of that spot that you guessed. So I'm going to keep factoring now. Just to show you, if I had guessed wrong, because often, so when you guess, I said you're going to guess factors of this last number 10. So if I were guessing, here's the order I would guess in. I would try 1, then -1, 2, then -2, 5, then -5, and then 10, and then -10. One of those is going to work. One of those is going to be a hit. Now, in this case, the first guess turned out to be a hit. That's not always true. If I'd gotten a number that wasn't 0 here, I would just do this exact same process again with this next number at the top, and then the next number, and then the next number until I got one that worked. So let's finish factoring this. I say, oh, look, this guy, so I already have this x minus 1 at the front. This guy has to have a 3x and an x, just like we saw in the other examples. I know the back seats have to either be a 1 and a 10 or a 2 and a 5. And I know from the plus sign that they have to have the same sign, and that sign right here has to be positive. So I want an 11 in the middle. I realize that the 10 and the 1 are not going to work, because the 10 opposite the 3 would give me a 30, which is way too big. And if I use the 10 here, I'd get a 10x and a 3x, which is not an 11. So I know it's the 2 and the 5, right? I realize that if I put the 5 opposite the 3, I get 15, which again is way too big. So the 5 must be here, the 2 must be here, and then I check real quick. My first terms would be a 3x squared, so that's right. My outer and inner would be a 6x and a 5x, that's a positive 11x, and my last seat would be a plus 10. So my fully factored form is this x minus 1 that I got from synthetic division, the 3x plus 5, and then the x plus 2. So that's my final answer. And that's a quick overview of how you want to do factoring.